This video will be talking about the inverse relationship between logarithms and exponentials. Okay, let's look at a particular example for this. So we're going to be looking at the exponential equation, y equal 3 to the x power, and we're going to be looking at the logarithmic equation, y equals the log base 3 of x. So let's look at some values for this logarithm. So if I place -1 in for x, if you have 3 to the -1, well, -1 exponent or a negative exponent just brings it to the bottom of a fraction and a 1 goes on top. So this is 3 over 1 or 1/3. If you put in x equals 0 into here, 3 to the 0 is 1 because everything to the 0 power is 1. 3 to the 1 power is 3. 3 to the 2 power is 9. And 3 to the 3 power, 3 times 3 times 3 is 27. All right, let's look at the opposite of that. So let's look at y equal log base 3 of x. If you have, if you put 1/3 in for x, log base 3 of 1/3 is equal to 1. -1. Or another way of thinking about it, 3 to the -1 is equal to 1/3. All right. If you put 1 in for x, log base 3 of 1 is equal to 0. Or another way of thinking about it, 3 to the 0 power is 1. Okay. If x equals 3, y equals 1. If x equals 9, y equals 2. If x equals 27, y is equal to 3. What you'll notice is their x's and y's are basically switched for each one of these. 1, 0, 0, 1. 3, 1, 1, 3. 9, 2, 2, 9. 27, 3, 3, 27. And that's because for inverse functions in general, they have their x and their y switched. So that's how you can sort of confirm that these two are inverse functions. If we're going to generalize this to logarithms in general and exponential equations in general, then you have this. So y is equal to log base b of x is an inverse to y equals base b of x. Pause the video, take notes. When you're ready, hit play. Okay, let's look at the graphs of these two functions we just talked about. So up here, let's draw the graph for y equals 3 exponent x, or g of x basically is like a y. So we know when x equals 0, y is equal to 1. So it goes through that point. When x equals 1, this here is counting by 1, so that's 1, 2, 3, 4. 1, 2, 3, 4. All right, so X equals 0, y is equal to 1. X equals 1, y is equal to 3. It's over here. X equals negative 1, y is equal to 1/3, which is about here. So going in this direction to the right, it goes times 3 times 3 times 3 times 3. Going this direction, it goes divide 3, divide 3, divide 3, divide 3, divide 3. So if I were to draw this, it looks something like that. Going towards the right, it increases very quickly. And coming down this way, as it's dividing 3, dividing 3, dividing 3, it gets closer and closer to 0. But it actually never reaches 0. On the other side, let's graph f of x equals log base 3 of x. And f of x here, once again, is like a y. And like we showed on the previous page, when y is negative 1, x is about 1/3. So right there. When y was 0, x was 1. When y was 1, x was 3. So if I were going to draw this, that's me connecting the dots. So once again, these two functions are inverses of each other. And one general fact about inverses is that they are reflected. So if you were to draw the line y equals x, so this right here is the line y equal x. Inverses the graphs of inverses will look like reflections across the line y equal x. If I kind of put this vertical, the left and the right should look the same. All right, so here our exponential was increasing the whole time. Anytime your base is greater than 1, your exponential increases, and then your log also looks like this, where it's increasing as well, going towards the right. Let's look at a different graph of two inverses. Here we're going to look at these two right here. This is an exponential. K of x equals 0.5 to the x power, or 1/2. And our inverse logarithm is L of x equals log base 0.5 of x. And once again, L of x is like a y. So let's look at what the graph for this looks like. Okay. So for this equation right here, once again, when x equals 0, y is equal to 1, so it goes through this point right here. When x equals 1, 0.5 to the 1 power, y is equal to 0.5. 0.5 to the 2 power, 0.25, or 1/4. 0.5 to the negative 1 is 2. 0.5 to the negative 2 is 4. So the graph is going to go through those points right there. So it looks like that. Going to the right, it's dividing by 2 each time. So it's getting closer and closer to 0, but it never reaches 0. And heading towards the left, it's multiplying times 2 each time. If we were going to do this, it is similar but not quite. When my x equals 1, my y will equal 0. Or when my y equals when my y equals 0, my x is equal to 1. When my y equals when my y equals 2, when my y equals 2, my x is equal to 0, 1/4. Actually, I should probably do, when my y is equal to 1, my x is equal to 1/2. When my y equals 2, my x is equal to 1/4. When my y is equal to negative 1, my x is equal to 2. And then x equals 4, y equals negative 2. So give me a second to connect those dots. So there you go. This is an exponential function that's decreasing or decaying. So exponential decay. And this is the inverse of that. That looks like that. And once again, because these two are inverses of each other, they will reflect across the, do a better job of that. All right, so these two functions are going to reflect across the y equal x line. So that red line here is y equal x. And if you look at the two graphs compared to this line, this side sort of looks like that side, because there should be reflections of each other over this y equal x line. Okay, so this is exponential decay, and the log, the inverse of that. This is what exponential growth looks like, and the log that is the inverse of that. For both of these, they're reflected over the y equal x line. The two sides should look the same, the left and the right side. And if we're looking at the domain and range of this, reminder, the word domain is what numbers can x be. The word range is what numbers can y be. So the domain of G of x equal 3 to the x power, the domain for that. What numbers can x be? Well, x can be any number. X can be negative anything or positive anything. So this is all real numbers. Range. What numbers can y be? Well, the y keeps on going up forever, and the y is going down, but it's going down by divide 3, divide 3, divide 3, divide 3. It never actually gets to 0. Here we're at 1, 1/3, 1/9, 1/27, 1/81st. It never, however, gets to 0 or to negative. For our logarithm, if we're looking at our domain, it goes to the right forever, and going in this way, it's going divide 3, divide 3, divide 3, divide 3, divide 3. It's getting closer and closer to that 0, to the getting, because this right here is 0, my hand, this line is 0. So it's getting closer and closer to the 0, the x's, but it never actually gets to negative. There's nothing on this side. So your domain is x is bigger than 0, and your range is all real numbers. Earlier in this video, I said that inverses in general have the x's and the y's switched. 1, 0, 0, 1, 3, 1, 1, 3. Because inverses have the x and the y switched, their domain is also switched. So the domain here was all real, so that means the range for its inverse will be all real. The range for this one was bigger than 0, so that means the domain here will be bigger than 0. Also, you'll maybe notice, this is true regardless of whether it is exponential growth or decay. So here, your domain is also all real numbers. Your range for this one is also y is bigger than 0, just like it's for this one. Same thing with our logarithm. Our logarithm here, domain were the x bigger than 0, range was all real. Same for this one. One thing you'll notice is that all of our logs, or I guess both of the logs that I just showed, went through this point right here, 1, 0. And our exponentials went through 0, 1. So in general, you'll notice that our logs are just going through that same point. Our logs will go through 1, 0, with the inverse exponential going through 0, 1. Okay, so this is a look at the graphs of logarithms and the graphs of their inverse exponentials. Pause video, take notes. When you're ready, let's move on. Hit play. So, let's continue exploring this. And let's look at the properties. So, because the exponential and the logarithms that we are showing are inverses of each other, there's a property that comes from that or stems from that. So if you end up having the log and the inverse exponential together, they will cancel each other because that's what inverses sort of do, or they undo each other. So this right here, this log base b and this exponential with base b, that stuff right there will cancel each other. And all you'll have left is that. So log base b of b to the t power equals t. And it works in reverse as well. Here you have the exponential b to the, and you have the logarithm log base b of, and this exponential and the log will cancel each other out, or they'll undo each other, and all you'll have left is your t. Looking at the examples we first did, where we were looking at log base 3 and 3 to the x power. So log base 3 of 3 to the x will equal x. On the flip side, 3 to the log base 3 of x will also equal x. One way of thinking about this is, let's put numbers to get a feel of this. So if I were to have x be 2, okay? So what is 3 to the 2 power? 3 to the 2 power is 9. Okay? So then what is log base 3 of 9? Log base 3 of 9 is 2. So here I started off by putting 2 in here into the x, and what came out at the end? 2. Or let's look at this one over here. Let's say that I put into this x right here, I put in, I don't know, 27. Let's do 9. Let's do 9, okay? So log base 3 of 9 is 2. So then what is 3 to the 2 power? 9. So I put in 9 there. 9 came out this side too.